It's my pleasure to introduce Dr. David Hurwitz. He is a professor of transportation engineering and the director of the Hurwitz Center for Infrastructure and Transportation Research in the School of Civil and Construction Engineering at Oregon State University. His research is funded by the Oregon Department of Transportation, the Crash Safety Research Center of Toyota, the American Automobile Association, the Murdoch Charitable Trust, which is funding an expansion of his research facility, and that's just to name a few. He's authored over 100 publications and was this year's recipient of the Graduate Mentoring Award from Oregon State University. Steve and I had the chance to meet David last year about this time. We went down to tour the facility and meet with another faculty member within that department, in part because of some research that I was applying for at the time is now funded to do some work looking at impairment and construction. And there's such a good group there. And with Emily's work in construction, I was like, this is really, we should make better use of our two departments and our strengths among the different departments. So I'm happy that David was able to come up this year and see further how we might make that happen. So without further, I'll turn it over to David. Thank you.
Oh my gosh, Nicole. Thanks so much for that lovely introduction and for the invitation to come and spend time with you all today. I could not appreciate your time more. So our overarching objective is to share a little bit more about traffic operations and safety research that's happening in the School of Civil and Construction Engineering. And really the thread that I tend to emphasize is one of transportation human factors. So I've got individual meetings with some of you this morning, with some of you this afternoon, but this might be my only chance to interact with some of the folks in the room. So I want to give you as much of a sense about what we do to help build future conversations. That's my goal today. In thinking about our research endeavor, I thought maybe a little bit of a logic model might be helpful. So I want to give you a touch of an orientation to some of the content spaces that we're currently working on. I'd like to describe a bit about our inputs into our research activities. Gosh, what it is that we actually do in the lab. Some of the outcomes that we've generated recently that I think are perhaps notable and opportunities to build on future successes. And then, gosh, hopefully to have a little bit of time for question and answer to think about how our interests might overlap moving forward. Okay, so a touch of orientation to our content space. So if you've never come across the idea of human factors as it relates to transportation systems, I'm very interested in thinking about measuring the abilities and limitations of transportation system users. And so that might take the form of pedestrians or bicyclists, passenger car operators, commercial motor vehicle operators, transit riders, any of the people that use our systems across any of the modes of interest. In particular, we have threads of emphasis focusing on heads and bikes, on commercial motor vehicles, and on connected and automated transportation systems. Those are three threads that are overemphasized in our work right now. We tend to apply that work in what traffic engineers describe as the operations and safety spectrum. On the operations side of the equation, we care about moving system users from their origin to their destination a little bit more efficiently. Reducing trip times, reducing the amount of time you spend in congested conditions, so on and so forth. On the safety side of the equation, we're trying to reduce the frequency and the severity of crash outcomes, trying to understand what types of crashes, what types of people are involved in crashes that are overrepresented, and then using that knowledge to mitigate those situations. My inspiration for joining this space, when I was an undergraduate student studying civil engineering, I thought I was going to build roller coasters. I thought that was the vision of this domain. And as it turns out, I'm not that great at structural engineering, and not that many civil engineers actually build roller coasters. My junior year, I didn't quite know what I wanted to be when I grew up, and I started working with my professors in their laboratories. And I did a little bit of work in geotechnical engineering, measuring the size of grains of soil through sieves. I did a little bit of work with environmental engineers, building weirs in the field to understand how pollution is increased during storm events. I did a little bit of chemistry in some laboratories, growing the media that cells might grow on, and I was terrible at all of those things. I finally stumbled my way into a traffic engineering lab, and the first project that I worked on was trying to ask the question, what happens when younger drivers are exposed to low levels of alcohol and get behind the wheel of an automobile. And we were studying this phenomenon in a driving simulator in the safety of a laboratory setting. And we were using police officers to measure the BAC levels of those younger drivers. And I was the undergraduate research assistant that got to play with the data from those experiments, and I've been hooked ever since. So I spent the last 20 years thinking about traffic safety in myriad forms. Okay. As it turns out, I've always loved the writings of Margaret Mead, a little bit of an inspiration for me myself. There's one quote that's always sort of landed in particularly meaningful ways. Never doubt that a small group of thoughtful, committed citizens can change the world. Indeed, it's the only thing that ever has. I think this perhaps might be more relevant in today's day and age than it ever has been before. I'm going to make a little bit of an edit here, so I'm going to modify that towards transportation professionals. And so people really are at the center of everything that I like to do in the transportation domain, and that applies to how we manage our research program as well. So inputs into our research investigations start with the people. And so this is my small team. So we mentor folks at the professional research level. So we have research assistant professors, lab managers, postdoctoral students. The bulk of our team are graduate students. So we have 10 MS and PhD students, usually split 50-50, about 5 PhD, about 5 MS, and then an army of undergraduate research assistants. I feel really strongly about giving folks who are early career the opportunities to have experience in laboratories, because that's how I ended up where I am. A very kind professor put up with me making all sorts of mistakes very early in my career so that I could be here standing in front of you all. All the work that I'm going to talk to you about today comes from these folks. I get to be the one here sharing these ideas with you, but it's our work collectively. We have to partner to solve problems in the surface transportation space. Our problems are incredibly complex, and we build partnerships with funding agencies in order to facilitate some of those outcomes. Nicole mentioned a few of the organizations that we work with currently. We've got an active grant with just about every program on the board here. We start with transportation agencies at all levels in municipalities. So we work with cities, county, state, and federal departments of transportation. Here in Oregon, we work with the city of Portland, with Washington County, with the Oregon Department of Transportation. At the federal level, we work with the National Highway Traffic Safety Administration, with FHWA, so on and so forth. We also work with industry and with nonprofit foundations. These relationships are incredibly important. Without resources, we can't have people. Without people, the work can't be done. Additionally, we partner with academic institutions, both domestically and internationally, of all sorts. Here's a handful of institutions that we're currently either writing journal articles with, partnered on research proposals with, collaborating over student mentorship, so on and so forth. The partnerships are incredibly important, whether we're bringing different bits of expertise to the table or different laboratory facilities or combinations of all of the above. And with a little bit of luck, we can add OHSU to this team moving forward. Beyond academia, we also partner with it. Sure. Sure.
This. You can take that one off. Thank you.
Sure.
Yeah, should we good to go?
Okay.
Just a quick test.
Test.
Yeah, a bit closer.
How close is close?
That's good enough. Yeah.
Sure, we'll make that work. Okay. Beyond institutions of higher education, we work with industry for a bunch of different mechanisms. One of those funding pools from the National Academy, the National Cooperative Higher Research Program, is particularly emphasizes partnerships between industry and academia. So companies like Tool or TalkCell or Kittleson tend to do research at a federal level, and we find that our ability to craft research questions and then translate them into design outcomes that are implemented can be advantaged by partnerships with practicing engineers. There's also a handful of companies here that help us build some of the technology that we use to solve those problems. Okay, so in addition to those items, I tend to be an experimentalist. So I love the idea of having experimental control and developing and applying the scientific method. I fundamentally believe in the scientific method, and perhaps it's silly to say that out loud in front of a room full of us, but I feel the need to state that publicly a little bit more often than perhaps I have in the past. So we leverage laboratory spaces to accomplish these outcomes. One of the labs that maybe we're a little bit known for is our human in the loop simulator facility. And so much like that lab that I started my undergraduate experience in, we model drivers and bicyclists and commercial motor vehicle operators in what some would describe as cave laboratories. So varying degrees of cab configuration with large screens that project rendered virtual worlds so that we can put real transportation system users in front of infrastructure of one sort or another. We have 4 simulators in our laboratory, a desktop development simulator. We use that to build experiments. It's computationally more efficient to code virtual worlds in those spaces. We then take our experiments from that dev sim and move it either into a full-scale passenger car simulator, a quarter cab commercial motor vehicle simulator, or a full-scale bicycling simulator. If there were 2 things I'd want you to take away from this representation of this laboratory capacity, stuff that makes us maybe a little bit novel as compared to other people who do this sort of work, these simulators are all networked, meaning a live subject in the bicycle simulator can interact with an avatar of a live subject in the commercial motor vehicle simulator at the same time. That's pretty novel. We're the only lab in the country that's doing work like that right now. So we lose a little bit of experimental control with that design. There's a second actor that can behave however they want in a scene, but we get a real response. And there are certain scenarios, crash likelihood scenarios, where we care a whole bunch about the interdependencies between multiple users at the same time. So that's one characteristic that's a little bit unique. A second is that the passenger car simulator and the truck simulator can function at different levels of automation. And so if you're interested in assistive driver technologies or fully automated control, we can model those in a lab setting and build better algorithms, design better human-machine interfaces to help advance some of that content space. And the footprint's a little bit multimodal in nature. Okay, so what does this look like in reality? Here's a little video clip from a National Academies project that just got published that generated a little bit of interest. This is our full-scale passenger car simulator operating under our old software environment. So this looks okay. The new software is pretty incredible. It's several generations of computing power more advanced. It's a much prettier rendering. This particular investigation was asking the question, how do we design bicycle facilities on the approach to signalized intersections to mitigate conflicts between turning passenger cars and the bicycle movement? We tested 18 different configurations of bike lanes entering through and across signalized intersections and recorded performance measures of our passenger car drivers interacting with those different designs and bicyclists traveling at different speeds and different placements. And the outcome from this work, what makes NCHRP kind of a cool mechanism in our space, is that those publications are endorsed by the National Academies and they serve as design guides for practicing professionals. So the recommendations from our infrastructure evaluation are now guiding state departments of transportation and other agencies in the construction of bicycle facilities at signalized intersections in the US. That's kind of a neat immediate outcome. In addition to the virtual world that is produced, we collect a whole bunch of data in these laboratories. The foundational measurement is an XYZ coordinate of the centroid of the vehicle that our subjects are interacting with, time-stamped at a rate of approximately 60 hertz. So we measure the location of the subject 60 times a second and then use that foundational measurement to produce all kinds of traffic stream performance measures that would be safety or operationally relevant. Think instantaneous velocity, lateral position, time to conflict, post-encroachment time. So representations of near misses, representations of travel speed, representations of placement in the lateral field of infrastructure. What we're looking at here is one of our former MS students, Kasia, demonstrating the truck simulator, some high-resolution cameras, validate placement of hand on wheel, placement of foot on brake and accelerator, and then the live streaming of some of those performance measures captured from the simulators themselves. In addition to the raw traffic parameters that are interesting to me as a civil engineer, we also collect physiological measurements. And this is something that might connect to some of you in this room. And so here are some examples of some of those measurement devices. In driving science, we tend to think a lot about visual attention. That's a really important measure. And so we use different techniques to represent eye movements that we can document visual attention from. So eyes move in one of two ways. Functionally, there are fixations and saccades. This is a head-mounted eye tracker, and that device measures empirically fixations. So it gives us an XY coordinate for a pause for some duration of time at a location in space. Those are our individual fixations. In driving science, we set that threshold at about 1/10 of a second. And so we build lists of fixations, and then we calculate the saccades between those fixations, and those two pieces describe eye movement. And when we're trying to understand how a subject is allocating maybe risk and hazard perception, one question is, do they see those risks in front of their forward field of view? When they're interacting with things like traffic control devices, do they look at the sign, signal, or pavement marking to acquire the message we're trying to communicate? And then what do they do with that information after they've acquired it? In addition, a little bit more recently, we've expanded into representations of, I'm going to call them stress. Some others might describe them as arousal, but using GSR, galvanic skin response, as a representation of attention, perhaps. And how that overlays with the driving task. Here's one example of one of our measurement techniques. We use a data acquisition system called iMotions as the foundational core, and then we connect a variety of sensors, whether it's a Tobii 3 Pro eye tracker or a Shimmer 3 Plus galvanic skin response sensor, in order to record the behavior of our subjects as they're interacting with the virtual world. Okay, so those are in-lab studies, but everything can't possibly occur in the lab, and we have to validate those laboratory experiments with other data measures. And so over the last couple of years, we spent a lot of time building up our quals in the naturalistic study space. Here are some examples of instrument packages that we have installed on vehicles for on-road field testing. That's a Vericom. It's a crash reconstruction tool that can connect to the onboard diagnostic system of the automobile, getting you some live streaming data from the car itself. It has a GPS system that allows you to extract instantaneous velocity and placement across roadway maps. This is an example of a triaxial accelerometer. We've done a bunch of stuff trying to measure the vibrations in vehicles and how subjects respond to them, so on and so forth. Here are examples of some studies that we've done recently implementing eye tracking on pedestrians to try to better understand where they're acquiring information in the field as they're making choices to cross the road. In addition to naturalistic studies, we leverage surveys to acquire larger samples, typically revolving around comprehension. We design a lot of novel transportation infrastructure, and trying to understand the best way to convey our simple messages for drivers or bicyclists in different contexts helps a ton. This survey was evaluating bicycle signal countdown timers, some conceptual designs before field implementation. So how do we convey to a bicyclist on the approach to traffic signal how much longer they're going to have to wait for that red light to turn green? If any of you ride bicycles, not the right audience for that. If you were to spend some, maybe sort of, kind of, maybe you've been on a bicycle before, maybe you're annoyed by bicycles at the roadside. Anyways, the city of Portland is a national leader in this space. They imported 32 Dutch-style near-side bicycle signal countdown timers from the Netherlands, and they installed them on Southwest NATO Parkway. So the next time you're walking around on the waterfront, those little 4-inch diameter bicycle traffic signals, spend a little bit more time looking at them. There's a countdown timer at the top of those indications that tells you how much longer the light's going to be red before it turns green. This is the only city in the country that has those. They're really cool. A guy by the name of Peter Kuntz made that happen. This other survey is evaluating a novel type of bicycle infrastructure. It's called a bicycle turnout. They were first installed in Mount Diablo, California. It's a mecca for bicycling. It's a ton of uphill, beautiful roadway environments. Thousands of bicyclists ride those roads every day. But there's also a lot of motor vehicles, and there were overtaking crashes in these constrained right-of-way spaces. They're short bike lanes that were applied to the outside of horizontal curves on an uphill portion where there was a lot of overtaking. They've never been used anywhere else, but they're immensely effective in mitigating overtaking crashes. This was a survey to evaluate their utilization here in Oregon. Okay, on the operations side of things, we use microsimulation tools to predict how traffic is going to function across roadway networks. This is a particular tool. It's called VisSim. It's a German piece of software that was brought to the United States for the first time about 25 years ago, interestingly, by an alumni of Oregon State. Thomas Bauer is his name, started a company in Beaverton, Oregon. He was the first one to bring this tool to the States. It's a way to represent how traffic interacts with pairs of vehicles at all sorts of different transportation infrastructure. This particular example is modeling how heavy trucks that are 26,000 pounds or greater, interact with gap acceptance paradigms at roundabouts. This particular study advanced the state of modeling for Oregon's DOT in some pretty useful ways. It's been operationalized as a standard moving forward. We also get really fancy with our microsimulation tools. This is a concept called hardware-in-the-loop modeling. We take the real computers that operate traffic signals in the field, and we connect them to the microsimulation environment to generate even more realistic models. This is an example of a corridor from Scappoose, Oregon, with 5 actual traffic signal controllers plugged into a VisSim environment to increase fidelity of the modeling characteristics of that environment. It's the only one in the country that functions the way that it does. And when it's working, it looks a little something like this. That's a lot of stuff that won't make a whole bunch of sense to just about anybody in this room. This is the software interface for the actual traffic signals in the state of Oregon. Q-Free is the company that we use for the entire state for all 10,000 traffic signals. What this is showing you is the actual status of each individual indication at that traffic signal, and the calls for service, and which lights are green, and which phasing status is going to change, so on and so forth. There's one of those running for every traffic light that you've ever driven through in the state of Oregon. This is a representation of 4 of them. You'll see them right down there. That's what VisSim looks like when it's live and running. Those green and red lights are the actual traffic indications for the individual approach. And this is a model of the entire corridor. When we coordinate traffic lights, we try and generate green indications in the direction of travel that we're supposed to optimize. So groups of vehicles can travel through those lights together a little bit more efficiently. These bands of blue and green are describing how the light structure will carry individual vehicles all the way across the corridor. Those little yellow dots, those are trajectories of simulated vehicles evaluating new phasing and timing plans that can be implemented in the field. So once we build all that hardware, we can test if novel phasing and timing configurations will improve the safety of vehicles on the corridor. There's some pretty cool ideas about using phasing and timing to manage speeds, to reduce the prevalence and the severity of crashes on corridors. This is one of the configurations where we have an overrepresentation of crash outcomes. So if we can time the lights better, maybe we can use that as a safety treatment to mitigate some of those outcomes. That's the point of all that hardware and software. Pretty cool. The system actually works, and we're giving it to the state agency. So the traffic signal engineers at ODOT will be using this tool for their coordinated corridors to try and mitigate some of those systems moving forward. We also try and measure in the real world what is happening. We do that in a couple of different ways. I've started playing around with drones over the last couple of years for a typical or unique transportation infrastructure. We've been thinking a lot about those big vehicles. They're also overrepresented in crash frequency and severity in particular. And so thinking about how they interact with transportation infrastructure might be a way to mitigate some of those outcomes. We've thought a lot about truck parking and the reasons why trucks don't park in the spaces they're supposed to park in. We've also thought a lot about how we design roundabouts in order to advantage better decision-making from commercial motor vehicles when entering and exiting those systems. That elevated perspective can be useful in a bunch of different ways. Here's a little ground truthing from that corridor in Scappoose, Oregon. where we modeled all the traffic signals and have proposed new phasing and timing solutions for the agency to try to improve safety. Additionally, we make observations at the roadside. We use all kinds of different sensor systems. These are a couple examples of some recent work. That's Dylan Horn, a former PhD student of ours, did his undergraduate and his master's from North Carolina State. He's measuring sound at the roadside using some relatively advanced microphones in order to understand the sound produced by car strikes with rumble strips. Rumble strips are amazingly effective to mitigate run-off-the-road crashes. In the state of Oregon, crash analysis suggests we return $92 for every buck we spend on a shoulder rumble strip. They work all the time in all instances, except if people live near them, they don't like the sounds they produce. And so we have placed rumble strips in places where the safety analysis suggests they'll mitigate the run-off-the-road crashes, and they have been removed because the people who live there know the director of the state DOT. So we have some problems. If we can make them quieter but still produce an effective response in vehicle, maybe we can mitigate that concern as well. Additionally, we acquire high-resolution video for all sorts of instances to define what people are doing on the roadway. And here we're using LiDAR guns to acquire speed measurements over footprints of about 1,000 feet or more. Okay. So what kinds of problems are we trying to solve with those inputs? Well, they're varied. One of my very first studies using the hardware-in-the-loop simulator was revolving around dilemma zones. Can anyone remember the last time you were driving a car and approaching a signalized intersection and the light turned yellow while you were driving towards that signal and you weren't quite sure whether you should stop the car or continue through? Does that ever happen to anybody? Yeah, sure. It happens to all of us. It's called the dilemma zone. It's a real phenomenon. There's a whole bunch of details revolving around it. But we first asked the question, how do we define this phenomenon? We care about it because when you make the wrong choice, you can increase your rates of rear-end crashes. If you stop short and there's a close following vehicle, that can cause crashes. In fact, it's one of the leading causes of rear-end collisions at traffic signals is that right-of-way transition. And if you incorrectly go when you don't have enough time, you can be exposed to more severe, higher speed, right-angle crashes. That's where the real safety problem comes in. So we want to understand how and why they occur, and in doing so, perhaps we can mitigate their occurrence. Oh dear. Okay. So we had been observing these in the field remotely and thought, gosh, maybe we could build an experiment in the laboratory to add some additional detail. Again, this is probably a visualization you haven't spent a lot of time thinking about. These are time, space diagrams. So we can represent trajectories in this two-dimensional space. Those trajectories give us a whole bunch of information about drivers' decision-making and behavior. The slopes of those lines register the instantaneous velocity. Lateral measurements describe time differences between two subsequent vehicles. Vertical measurements are space distances between different vehicles, their headways. We can use all of that stuff to design safer signals. This is a series of experiments where 30 subjects were exposed to the onset of the yellow indication at different locations. This is two representations from that experiment. One where all the drivers were really close to the intersection when the light turned yellow, and oh my gosh, they all went through. Here's another representation where they were all quite a bit further away from the intersection, and just about everyone slowed down and stopped, although there are two trajectories that keep going through that intersection, one there and one there. Those folks actually ran the red light as the first experiment we ever ran in the lab, and it's the only time we've seen somebody run the red indication in that simulated environment. And so here's the part that's really interesting. This is one single subject from that experiment exposed to 11 different time to stop line activations of the circular yellow indication. And so when this subject is closer to the intersection, they clear. When they're further away, they slow down and stop. And somewhere in the middle, something really interesting happens. They're a little bit close to the intersection. They choose to decelerate and stop. They're a little further away, and they choose to clear the intersection. Two different choices, with opposing stimuli. Those are representations of the dilemma zone for this particular subject. Oh my gosh, it's a real phenomenon, and people can make perhaps incorrect or at least inconsistent decisions. Well gosh, how do we mitigate that? And so there's a bunch of different ways that we might be able to solve this human decision-making challenge. One is provide different forms of information. So we've studied human-machine interfaces either attached to vehicle tech in the cab or infrastructure in the field. Think countdown timers as an example. We could use more inventive signal phasing and timing. What if we had real-time detection that could show us the placement of those vehicles, and we extended the all red indication to clear that late entering vehicle so they wouldn't be exposed to the conflict in the traffic signal? That's an actual design that we built for the state agency that's running on a half a dozen intersections here in town. We can also modify phasing units. That was a National Academies study that we ran on change in clearance intervals related to protected permitted left turns. If you've ever seen a flashing yellow arrow in the state of Oregon, we were early adopters of that technology, and we've built recommendations for how to implement it with greater degrees of safety. Yeah, question? Sure. No, it's a great question. So there's laws in every state related to how you're supposed to respond to a circular yellow indication. That's the starting point. As it turns out, they are not consistent. So every state has a slightly different standard. Some are consistent, but there's sort of three bins of policy statements. They're all a little bit variable and would result in very different responses to that circular yellow indication. Second part of the question is, how are they timed? There is an equation, up until 2 years ago, it was called the kinematic equation. Now the standard recommendation is an extended kinematic equation. It takes into account characteristics like the speed of the vehicle, the grade of the roadway, the perception reaction time of the driver, so on and so forth. It's a physical representation. There's a ton of debate if we got the physics right on the extended kinematic equation, but it's also not required nationally. So some people use it, some people don't. There's a distribution of alternative timing strategies. So no, not timed consistently. So variable policy, that's part of the problem. Variable timing units, that's part of the problem. Human perception of speed and distance is not great. That's part of the problem. And our comprehension of all of the above is skewed. So there's a lot that goes into not generating correct outcomes here. Question? Yeah. Mm-hmm. Yep. Yep. It's an exceptional. Yeah. So the fundamental question was, first question was, how do we time yellow light duration? Second question was, is there a timing unit that we could apply that would prevent the conflict for cross traffic, potentially by extending the red indication? So the answer is yes. We call it the red clearance interval, the red clearance interval. Some people would describe it as the all red phase. So it's a timing unit. In the state of Oregon, they tend to run between 1 and 2 seconds, 1 and 2 seconds on average. They've been around for quite a while. There is no national requirement on its duration. There is a timing calculation that we apply. It's part of the kinematic equation. So there's a piece of it for time in the yellow change interval, the yellow light, and there's a piece of it for time in the all red. The variables that we've input into that calculation have changed over time. They include an approximation of vehicle length, the width of the intersection, the speed of the approach, so on and so forth. There's some argument over which characteristics we should include. the history of that timing unit has evolved to consider the width of the leading and following crosswalks as examples. Those will come in and out of favor depending on the design of the individual intersection. What you described in Texas is incredibly important. The longer those safety intervals are, the more likely it is that drivers will disobey them. So that idea that Texas runs a 5-second duration is for sure true. As it turns out, everything is in fact bigger in Texas. So they run really long cycle lengths, like 300 seconds, longer than you would ever see in the Pacific Northwest. And we get into arguments over those choices all the time. If you make them too long, you increase driver disobedience. And in fact, any traffic control device that you place in the built environment, the foundational implication is, one, is it serving a purpose that is needed? And two, a negative outcome from every single traffic control device is it will increase driver disobedience to a degree, because not everyone is going to do what they're supposed to do all the time. So you've got to be solving a problem with those treatments in order to place them in the field. I'm a huge believer in the all red phase. I really do think a factor of safety is important, but we have to be cautious not to simply increasing the timing unit length doesn't produce a safer outcome, because you'll drive up your red light running and then you're going to have a different type of crash outcome. We use the same logic when we thought ABS braking systems were going to solve all crashes. When those came out, same thing with seatbelts, same thing with airbags. There is a margin that's saved from each one of those systems, but some of them also produce shifts in driver behavior. So we thought ABS brakes would prevent all crashes. And instead, what we did was we followed more closely than we used to without them, because we can stop faster. So there'll be a dip. If you look at the epidemiological perspective, we'll have a reduction that's measurable, and then it's going to be problematic. It'll come back, so on and so forth. That's a really good point. Okay, I'd mentioned that we've been thinking a lot about trucks in roundabouts. I thought I'd give you a couple of numbers that were particularly compelling recently. We did a field study of big trucks in Oregon and their gap acceptance behaviors at roundabouts, because larger, heavier vehicles require larger gaps in time and space from conflicting passenger cars. So when roundabouts have congestion, they delay big trucks. And so you can quantify this by counting the durations of gaps that trucks are exposed to, tagging them as either accepted or rejected, and then building distributions of those performance measures. And nobody had ever taken the time to do this because it's incredibly time intensive and annoying. But what we see when we quantify this is that as the size of the truck increases, the length of the gap required to be accepted also increases. Maps our conceptual understanding, but nobody had wrapped numbers around that. The measure that's even a little bit more interesting is the critical gap. So that threshold for an available gap whereby 50% of drivers exposed to a gap of that length would accept it, 50% would reject it. It accounts for all of the decision-making characteristics. And what we see on a per truck configuration basis is that that critical gap ranges between 5.4 to about 6.2 seconds for WB40 to WB92D size trucks. Think big articulated tractor trailers. This is fascinating. Those gap lengths are about 2.5 times longer than that a passenger car would require under similar conditions. And that's data that we didn't have before. Those measurements have been baked into microsimulation standards in our state for more accurately predicting the characteristics of operation performance. We've also spent a bunch. Please. No, you're fine. Yes. Yeah. The 50% thresholds. Yeah. If you watch the video from the behaviors, there's a couple of things that are interesting. So that's one of them. At some point, they just nudge their way in and force the circulating traffic inside the roundabout to yield to them. In some instances, passenger car operators seeing a 150-foot-long multi-unit tractor trailer recognize the fact that that truck is not going to be able to enter this roundabout, and they'll yield the right-of-way. So, which is interesting from a perspective of being neighborly and trying to advantage someone else, like that's great, except they're violating the law in doing so, which produces an unexpected behavior in the traffic stream, which can drive up rear end crashes. So one of the mitigation techniques that's been tried in some places is evaluating a policy that says, under congested conditions, it's okay for circulating traffic to yield the right of way to that approaching truck in violation of the signing and marking for a roundabout. That's one solution that's been tried, and it's something that our agency is thinking about a little bit. We don't have a ton of roundabouts that operate under congested conditions. Our trucks don't tend to wait all that long, but it has the potential to be a problem, and as volumes increase, it'll get worse. So we thought about policy mitigations that could advantage those trucks to make those movements a little bit more efficient. We also played with geometric design modifications and operational modifications that could also advantage those trucks using technology in slightly better ways. Thinking about safety in large commercial motor vehicles, if you were to plot crash outcomes geospatially and relate them to the prevalence of parking facilities, what you would find is in the absence of available truck parking, crash outcomes increase. There's a suspicion that fatigued driving is contributing to some of those outcomes. And so there's an infrastructure component to this. This is the rest area at the North Santa Ana truck stop. And there was a suggestion from trucking companies that the parking here was ineffective and that they were instructing their drivers not to park where they were supposed to. Those kind of qualitative observations can sometimes be indicative of real problems, but I'm a data guy. I wanted to prove this, not just talk about it conceptually. And so we got access to some logistics information. And this is a pull from a digital logging company that helps CDL drivers manage their time in service. Each one of those dots on this map represents a pause at an XYZ coordinate of 10 minutes or longer. And so this is that same North Santa Ana rest area. And so the parking spaces are here and here. And gosh, what do we see? We see trucks parked at every part of the road in addition to those parking spaces. This is important because strikes with parked vehicles within the cross-section of the roadway are also overrepresented in serious crash outcomes. Every time a vehicle parks in the cross-section of the roadway, they become a fixed object in a place we're trying to remove fixed objects from. If we park there, eventually we will be struck. And so these are trucks parked in the shoulder on the roadway in both the northbound and southbound direction, on the on and the off ramps. That's a problem. That is not ideal. And so our little piece of intervening in this was to try and help engineers at the agency design better striping so that those commercial motor vehicles would use the spaces that were intended for them. Even if we provided fewer spaces that were used with greater frequency, we might be able to mitigate this problem just a little bit. And so this was an application of, think of it as a usability study. Design engineers who had no standard for truck parking were able to play with some different design alternatives and then interact with those in a virtual space in a commercial motor vehicle, which they also did not have any experience operating, in order to arrive at a better design standard. And so this was a technique that the striping engineer used to arrive at a preferred alternative. Frank is the line engineer for the state agency, and he has overcome a myriad obstacles, including some just terrible training as an undergraduate student in his highway engineering class. Here's an example of those bike signal countdown timers that you're all going to be paying attention to the next time that you're on the Southwest NATO Parkway. This was a pretty interesting intervention. And so the motivating factor here was, could we reduce red light running from bicyclists by providing them with countdown timer information? And so we tested 5 individual locations here in town. And as it turns out, shockingly to me, we drove down the likelihood of red light running substantially just by providing a little bit more information about how much longer the timing unit was going to be red. We've tested dozens of different types of bicycle infrastructure. There's all kinds of confounding factors that influence a cyclist's decision to stop, go, pick a certain speed. I was shocked that an intervention of this scale would produce that kind of outcome, but it worked really, really well here in Portland. So we're hoping that that's going to scale a little bit more. I got asked to give a presentation to the Canadian Manual on Uniform Traffic Control Devices in about a month about this project. They want to see them in Vancouver, British Columbia. So hopefully we'll get a few more test cases internationally. Okay, so what are some example outcomes from work of this sort? Here's a couple locally in the design standards space. So our team co-authored the ODOT Safety Investigations Manual. This is the practices and procedures by which traffic safety investigators analyze crashes in the state of Oregon and produce recommended mitigations. So that went live in 2022. We also designed a couple of new traffic signal heads. So Dr. Hisham Hisham is a research assistant professor in our group. His dissertation was proposing this and this traffic signal head. So applying those flashing yellow arrows that Oregon's been using since about 2001 for permitted left turns to permitted right turn applications. Turns out drivers yield the right of way to conflicting bikes and peds with dramatically higher rates if they're provided that indication as compared to others. So that was a pretty neat one. And then the micro simulation standard for the state adopted all of those commercial motor vehicle recommendations from modeling big trucks in roundabouts. Okay, so that's design standards. What about new technology? We've mentioned a little bit. That was one of the first Dutch-style near-side bicycle signal countdown timers. Our groups also helped develop blue light bicycle detection feedback systems. If you've ever been driving around the city of Portland and seen a little 2-inch blue light kick on while you're navigating the built environment, those are to communicate to cyclists that they've been detected and that they're going to get a call for service. We modified some of those designs at about 30 intersections and gave them a little bit of supplemental signage. They're in Portland, and Salem, and Corvallis, and Eugene. Good indication for pilot studies like that is the traffic engineers didn't take them out after they installed them. So those are still live and in color. This is in Washington County. It was the development of a dynamic pedestrian extension and cancellation system. We're using FLIR detection to observe bikes and peds crossing a mid-block crosswalk in real time and extending the pedestrian walk indication if there's a late entering, slow-moving pedestrian to avoid conflicts with through-moving traffic. We can also, from the efficiency side of things, cancel a call for service if someone pushes the push button and then jaywalks and clears the crosswalk. So we worked with friends at Q-Free and Polera, the folks that build the hardware that runs traffic lights, and then friends at Washington County to implement that system. They liked it so much, we're studying an extension of that at a 4-way signalized intersection right now. And then there's an example of our rumble strip designs that got adopted by the state as their preferred mechanism. I mention this because I think it's really important for all of us that are doing really good work in the science and health space to talk about why the scientific method matters and why findings are helping society. So every now and again, when folks are interested in traffic safety, we try and share good messages about what research is producing in the world. There's also this piece of public policy. A couple ideas came up when we were talking about yellow lights. We did an investigation pretty recently that was kind of interesting, especially for those of us who live here in the Pacific Northwest. Bicycle rolling stop laws as an idea originated, believe it or not, in the state of Idaho in 1982. It's a differential law. It says if you're on a bicycle and you're approaching a stop sign, you can treat it as a yield. And if there's no conflicting traffic, you can continue moving through the intersection. That started in 1982 and kind of nothing happened for a couple of 10 years. About 10 years ago, other states in the U.S. started thinking about these bicycle rolling stop laws. There's 11 states, 10 states in the District of Columbia that currently have a version of this law in the books, and Oregon's one of them. When we adopted this law a couple of years ago, there was some concern from the Traffic Safety Office. Is this going to make people less safe? As it turns out, the answer is absolutely not. This was the first real application of our networked bicycling passenger car simulator space. We put 2 real users in stop-controlled intersections and had them interact with one another under differing definitions of the bike rolling stop law. And as it turns out, bicyclists do not make less safe decisions just because they're allowed to treat a stop sign like a yield. they see fast-moving 3,000-pound cars and yield the right-of-way to them if they're too close. This is cool because this law is being debated in state legislatures all over the country right now. The state of Vermont, New Mexico, and California are currently citing some of our research outcomes in policy positions in front of the state legislature. Okay. With that, I'll go ahead and pause, and maybe we could transition into some questions. Yeah. Yeah. It's an exceptional question. So the question, so the question was, would yellow light runners or amber gamblers apply different logic to their decision making under varying weather conditions? So those cave-based simulators, we can render different environmental characteristics. In our older software environment, the version of the video that I shared with you here, we tended to avoid it. It wasn't particularly authentic. So almost all of our studies up until now, we had not used those characteristics. With the new software that we've launched, this is a pretty big upgrade. So we put about $2 million into computers and hardware and software. We built a building, and we kind of just got it all running like a week and a half ago-ish. We're doing some stuff for the National Academies on pedestrian safety under nighttime conditions at mid-ball crossings. If you're interested in ped and bike crash outcomes in the last 10 years, normalized on any factor that you care about, they're getting worse and worse. Crash outcomes in general, but peds and bikes disproportionately. And 75% of those increases are happening under nighttime conditions. So we just finished a study for the National Academies, 1797, on ped safety under nighttime conditions, testing different engineering treatments and yielding behaviors of approaching motorists at different speeds, while varying the skin pigmentation of the pedestrians at the roadside. So we've been trying to think about genuinely equity in non-trivial terms in some of our research. And this was one of the first studies that we thought we maybe integrated it in a way that was meaningful. And so that work's being finally reviewed by the panel and will be published, but it's going to be design standards on how to improve safety for all kinds of PEDs under nighttime conditions. And so we modified things like PED refuge islands, so the physical barriers in the middle of the roadway, high visibility crosswalk markings, RRFBs, rectangular rapid flashing beacons, and human scale lighting as infrastructure interventions to try and improve yielding rates and yielding distances and decelerations in response to heads queued at the roadway, to make recommendations on how to systemically improve at least one element of those crossing outcomes. So super important. It maps to crash outcomes in all kinds of different ways. And with enough fidelity, I think you can do some pretty good stuff in that space. And we're probably about there in the cave-based environment where that might be a lever we can pull on. Yeah. Yeah, that's a great question. A little bit. So sure, the question was, how do driving safety behaviors in Oregon compared to other states across the country? The project that we're working on right now that's the closest in that space is for the AAA Foundation for Traffic Safety. This is maybe our second study that's got an equity lens. We're looking at crash data in Oregon, in North Carolina, in Maryland, and in Arizona. So 4 states, pretty robust representations of crash data with varying driver demographics and crash outcomes. So of those 4 states, the greatest overrepresentation of crashes is in North Carolina. And so one foundational question is, oh my gosh, why? The rates are dramatically higher. They're one of the worst in the country. And so we're looking at all kinds of different contributing factors to those outcomes, and a variety of different data sets. Maybe one that might be of interest to this audience, we're mapping crash data information against EMS records to start to add some of the medical outcomes in addition to what's observed on site by police officers. So what does the medical treatment look like from the point of that crash to the trip to the hospital? It's not the full picture, but it's a little bit more robust than what we would have in licensing data and in crash and accident information. And so if you spend time digging into those records, it starts to tell us a little bit about travel time and some of the interventions that are administered inside to the hospital, and a little bit more detail in terms of at least the preliminary assessment of injuries observed. And so there's a couple of observations in that space from some recent work. Yeah. Yeah. Uh-huh. Yeah, that's a really important question. So for traffic circles, did we evaluate the difference between single lane and, yep, and dual lane roundabouts? So for the work that we did, we picked single lane specifically because it's the most conservative geometric configuration. So for those big trucks and their operational characteristics, things like the off tracking, how the edges of the vehicle overlay with the path of the wheels, the biggest worst effect, the most conservative condition is the single lane condition. So for that study, we focused on that alone. We're doing some work right now on passenger car conflicts and bike behavior in over-designed roundabouts in Washington County. So they're a little bit more rural than some that we looked at, a little bit lower volume, but they're designed to be built out to 2 lanes, although they're striped for 1 lane. And one of the things that we're finding is the whole reason to use a roundabout, at least in our state, is to mitigate crash outcomes. There's 32 what we call conflict points at a standard 4-way signalized intersection. There's only 8 in a roundabout. And all the conflict points that we eliminate are the more severe conflicts. The right angle stuff goes away. It's all merging and diverging conflicts. So the frequency of crash conflict is reduced and the severity of the outcomes when they happen is lessened. So they're really good from a safety treatment. There's like 310 roundabouts in our state, and almost every single one of them was installed with the motivation of improving safety at that location.